Okay, now let's look at an example problem to learn how to apply this ranking theory. So here we have a retaining wall, and on one side it has just sand, on the other side it has sand, and on top it has some clay, and on top it has some other load that is maybe like a small building or something. So, and we have the soil parameters given, and there is 6 meters of clay supported by this wall, and then there's 4 meters of sand at the bottom. So the question is, check if the wall can resist, or if the system can resist failure by analyzing or forces, assuming wall translates to the right. So now our wall is going to move in this direction. That means everything on the left side will be active forces, and everything on the right side will be passive forces. And then if active is bigger than passive, yes, the wall cannot resist that. So actually before that, let's consider if this wall wasn't moving at all, we would have K0 condition on both sides, but then you would have a force imbalance because on this side you have more and the K0 values would be the same for this side. So, but the vertical stress is larger for this left side. So it will simply be pushing the wall to the right. So that is the at rest case. So that says this wall cannot stay in place. As it moves, you are reducing the forces on the left side, you are increasing the forces on the right side, so you are going towards equilibrium. So if you are able to reach equilibrium, that's fine. If you cannot, then the wall fails. Because at active versus passive state, those are the extreme values of the stresses. The stresses on the left cannot theoretically be less than the active values, and the stresses on the right cannot theoretically be greater than the passive values. So if the passive forces are still less than the active forces, then the wall fails. So let's see what we can do with this. In short term, let's say, I have to say that because that's how I will know I need to do the undrained analysis for the clay. Of course, in this question, only the undrained strength is given, but anyway, for the sake of completeness, because I could analyze this for long term as well. So for short term, I will analyze clay as undrained. Sand will always be drained. So I have the friction angle for that. So let's begin. And because it is simpler, let's start with the passive side. So for the passive side, and I'm going to do this by, again, as usual, plotting stress variations. So I'm going to first plot my vertical effective stresses. So my vertical effective stresses on this side, on the passive side, or right side, are as such. I have 0 at the surface, and then 4 times 19 minus 4 times 10, or 4 times 9, I have 36 down here. I'm not going to show how I do these anymore because actually, just for the sake of completeness, let's do it this way. Let's also show total stress is 76, as we have space here. My pore pressures are going to be less. They are 0 to 40. And then my effective stresses are going to be the difference. So it is 0 to 36. Now next, what I'm going to have is sigma horizontal passive, because now remember, we are moving this wall in that direction. So the wall is moving towards this soil. The wall is compressing this soil in the horizontal direction. So the mode has to be passive here. And let's remember how to calculate the passive stress. It is sigma vertical effective stress times Kp. We don't have cohesion, so it's simply this, Kp times sigma vertical. So we need to calculate Kp, and Kp is 1 plus sin phi over 1 minus sin phi. So if you do that calculation for sand, you get Ka for 30 degrees. 1 minus sin phi is half, 1 plus sin phi is 1.5. So you get 1 over 3 for Ka, and for Kp, you get 3 for the, so let's write those fully. Ka is 1 minus sin 30 over 1 plus sin 30. So that is 1 over 3, and Kp then is 3. So Kp is 3 means you just multiply everything you see on the vertical side. With Kp. So what you get then is from 0 to 108. And if you want the total stresses, total stress distribution here is going to be that plus the pore pressure. So you get 0 to 148. And then you can calculate the resultant for that. By the way, here for this particular problem, you can, from now, you can tell the water is going to cancel on both sides, because on both sides we are going to have some effective stresses, and then plus water on both sides. The water is equal on both sides. But you can, I'm not going to do that, because in some other problems it is possible to have unequal water. So you can actually have flow and then different water pressures. You can still do this, because thanks to our flow chapter, thanks to what we have learned in the flow chapter, you are able to calculate what the vertical stress is even with the flow, and then you can from there as well you can calculate the horizontal stress. So anyway, if this is the case, then this is going to be my let's call it passive force or passive resistance. So my passive resistance here is going to be this area. So it is 148 times 4 over 2, 296 kilonewtons per meter into the page. So again, this is a 2D analysis, just like when we were dealing with flow nets. Because it's a 2D analysis, everything you calculate is going to be per meter into the page. So that is the passive side. Let's look at the active side now. Now the active side is going to be a bit more complicated because I have more things there. So let me draw some for the left side. Let me draw a few lines here. Yeah, that should be good enough. So here is my sigma vertical, the total vertical stress. It starts from 30. And then where does it go? 6 times 20 unit weight. So it starts from 30 and goes to 30 plus 120. So it's 150 here. And then I have another 76. So this is 2 to 6 down here. My pore pressures are simply 0 to 40. Therefore, I can plot my effective stresses as $30 to $150 up here. Actually, in the clay, I am supposed to have some capillarity as well. So actually, I don't really need to consider this bit because in the clay, I'm going to do undrained analysis anyway. So this will be total stresses. And then down here, it is going to be, so I'm going to do total stress analysis. So I don't need that bit. But down here, I'm going to have 152, 186. So next, I have to consider so if I'm going to do total stresses up here, I don't need to consider effective stresses there. So this, again, here, I'm going to be doing total stress analysis, so I don't need to do anything there. Down here, my effective stresses, horizontal effective stresses will be Kp times effective stress. So what I'm going to have is 150 divided by 3 and 186 divided by 3. divided by 3 is the Ka. So I get 50 here, and I get 62 here. Then let's convert this to total stresses. Now up here, what I'm going to have is now I'm doing the total stress analysis. I know the vertical stresses, total vertical stresses. So this is going to be vertical stress minus 2Cu. The active stress is, remember, vertical total stress minus 2Cu for the total stress analysis. So what does that give me? That gives me at the top 30 minus 2 times 40. So it starts from minus 50. And then at the bottom it is 150 minus 2 times 40. So what you get is something like this basically. Minus 50 here and 70 here. So what does that mean? As I said, this means this doesn't exist. Here you have tension crack. So your actual distribution is 0 here because tension crack means it's separated from the wall. So the wall and the soil aren't touching each other anymore. If they aren't touching each other anymore, there's no stress. It is just 0. And then the rest is like that. Well, in order to calculate forces, I will need this length as well because it's no longer the entire 6 meters anymore. It is just some length here. So I need to also calculate how tall is this. And you can do this in 2 different ways. You can either consider similarity of triangles, name x here, 6 minus x. So x to 50 is 6 minus x to 70. You can do that. Or I know that this slope is unit weight of clay, 20. So I can figure out, because here I had sigma vertical, which has a slope of unit weight. So this also has slope of unit weight because this sigma vertical minus a constant. So I have 50 to cover, 50 stress to cover, and I'm going with a slope of 20. So I can calculate this is 2.5. Is the depth of tension crack. Next, I reach the bottom end where we face the sand. Now for sand, I already calculated the effective stresses. So from there, I'm going to do the effective stress principle. So down here, up here it is in clay, sigma horizontal active prime plus U in sand. So down here, what I'm going to do is it will start from 50 and go to, let's see, 62 here, 40 here. So go to 102 down here. So now these are my total stresses acting on the wall. By the way, in some cases you can see that if you have a tension crack and it is below the water level, or maybe it is raining or surface water comes in, and sometimes they tell you assume the crack is filled with water. Then you just put a hydrostatic water pressure into this crack. So then there would be from 0 to 25 a little triangle here. So that's also a possibility. Here there is no information like that. The water table is down here, so there isn't any need for water up here. The question doesn't say anything like that, so I'm not going to do that. Anyway, so now this is my this is going to be my active forces, and let's name it FA, active forces. And if I calculate that, it is 70 times 3.5 over 2 from the upper triangle, plus I have a trapezoid that says 50 plus 102 over 2 times 4. So I actually haven't calculated that. Let's see. 70 times. Actually, only the bottom side, only this will be 304, because this is 152 times 2, 304. So this will end up not being stable. So this gives me 426.5 kilonewtons per meter. So what do you see there? The forces on the left side pushing the wall are greater than the maximum possible resistance, or the smallest possible force on the left side is the greater than the largest possible resistance on the right side. Therefore, this wall will just fail. Of course, you could add little engineering details to the question. For example, I could say, if you are going to put one support, if you are going to put supports that carry this much, what should be their horizontal interval? So then the the difference between the two has to be carried by that support. So it is about 130 basically. So for every meter into the page, you need 130 kilonewtons of extra support from some other strut or anchor or some other element. So this is basically it.